And in this tutorial, we are going to cover the history of this promising paradigm, the taxonomy of widely used methods, cutting-edge algorithms, and downstream applications. And I'm He Mingxia, a PhD student from the Hong Kong Polytechnic University. And this is Yongqi Li from PolyU and Chen Liu from TikTok. Okay, let's get started. We express our sincere thanks to our team members, Chen Xiaodu from CA Lab and Maggie Wenjie Li from the Hong Kong Polytechnic University. We thank them for their hard work and collaborations with us for the preparations of this tutorial. And here is a QR code of our tutorial homepage and the Q&A website. You can find related papers included in this tutorial. Our homepage, and during or after the tutorial, if you have any questions to ask or any exciting ideas to share with us, feel free to read the question on the Slido website. Okay, and now let's get started to the first part of this tutorial. Well, nowadays we are experiencing an era of AI services during which various kinds of large language model backbones have emerged. And to raise for unexpected AI performance and towards artificial intelligence, the size of large language models and the computing resources required to train these models have increased rapidly. And this year, with the release of O1, OpenAI introduced a new direction for AI for artificial intelligence, which is test-time compute scaling. And as noted by Jim Fan from NVIDIA, the focus of computing resources is shifting from pre-training stage to the inference stage. By utilizing more tokens during the inference stage, we can perform reasoning, reflection, or self-correction. While large language models can explore a broader range of strategies and reasoning paths to reach the final answer and eventually converge to the desired solutions. Well, however, considering both the increase of large language model sizes and the test time scaling, we could see that the demand of efficient large language model inference is becoming more and more urgent, right? For example, as shown on the right, for a single input query, the inference time of O1 can take up to 3 minutes. To enhance AI services and reduce user waiting times, we need more efficient inference strategies, right? So here comes our first research question. Why is the inference of large language models so slow? Well, the first and the simplest answer lies in autoregressive decoding. Autoregressive decoding is the most widely adopted decoding strategy for decoder-only large language models. Or we could say that nearly all large language models use autoregressive decoding to generate their outputs. The advantage of AR is that it generates token by token, so that when generating each token, the large language model could refer to its previous outputs. Well, that ensures the quality of output sentences is reliable. And additionally, AR is quite easy to train and scale. With teacher forcing, we could utilize the ground truth sentence as previous outputs and calculate loss on all tokens in parallel. Well, however, the token by token generation behavior of AR makes the inference process very slow, right? A token will not be decoded until all its previous tokens have been generated. And with autoregressive decoding, the inference latency of large language models increase linearly with output sentence length. Well, if we decode 1,000 tokens, intuitively, we will spend 1,000 times than decoding just one token. And when we take a deeper look at the large language model inference, we can see that large language model inference is primarily memory bound. When we host a large language model with 13 billion parameters for inference, we will find more than 90% of GPU memory is allocated to storing the large language model parameters and KV cache. And during each decoding step, the huge number of parameters need to be transferred from the GPU HBM to SRAM for computation. And the limited bandwidth of GPU HBM, like as shown here, it becomes the primary latency bottleneck of each decoding step. In other words, the inference process spends too much time on reloading large language model parameters than performing arithmetic computations. Well, these figures from our paper in 2023 provide a more vivid illustration of this bottleneck. For example, when we host T5 large for translation, like in the first table, the average latency is 1 second of each batch, which reaches the user tolerance, right? But the GPU memory and utilization is far from full, only 4% of GPU utilization. And we're hosting the same time, the same model on summarization, which requires a larger output length. The latency is near 3 to 5 seconds, while the GPU memory and the utilization is still under 15%. In other words, the latency of large language model inference is reaching the user tolerance, while we still get large room for GPU utilization and memory. So we would like to ask a question: how to accelerate the large language model inference losslessly? And this question contains two meanings. The first meaning is that we would like to accelerate the inference process, right? And the second is that we hope the performance to be lossless. We do not expect any performance degradation through the acceleration process. And here is an intuitive insight from this paper in EMRP 2023. Well, in this figure, we can see that in a normal text paragraph, the tokens can be divided, or the words can be divided into different parts, right? The tokens in deeper colors, like the red ones, they maybe they contain the key information, the semantic information of this paragraph. And the tokens deleted, or tokens in lighter colors, they may contain unimportant information, or they may be just connectors between the keywords. And we can just filter out these tokens, these unimportant tokens, to keep the key information, the semantic information of the whole paragraph. Or in other words, in a paragraph, the tokens can be divided into simpler ones and difficult ones. And maybe we do not need a large language model to generate all the tokens. We can just use a very large language model like Llama 70 billion to generate the difficult ones and utilize a simpler and efficient language model to deal with the simpler ones. So this is exactly the research motivation of speculative decoding. How about we just use a small language model to do the easy part to generate the simpler tokens? And this is a vanilla demonstration of speculative decoding. Well, in each decoding step, speculative decoding first utilizes a small language model, like in the left, an efficient one to draft multiple tokens. And these draft tokens, like the yellow tokens in the left, and the green part here is the prefix or the input prompt of the language model. And we can use the draft token, use the small language model to generate a few of draft tokens, like 4 draft tokens in this figure, for example. And these draft tokens can be seen as speculations or guess on the future decoding steps of the target language model, like the bigger ones in the right. And then the target large language model, it means that the model we want to accelerate, for example, the Llama 70 billion, and the target large language model will verify all the draft tokens, the 4 yellow ones, in parallel in a single forward step pass. And if we get very lucky, if multiple draft tokens pass the verification, It means that we can get multiple tokens to be decoded in a single forward pass of the target large language model, or a single decoding step, so that we can accelerate the inference process like by 4 times in this example. If the draft process is very efficient, we can ignore its latency. And in practical, we will find that the draft model, the small one, it always hits simpler tokens. And the difficult tokens are more likely to fail this verification process and to be generated by the target large language model. And in the following, we provide a detailed illustration of a single decoding step in speculative decoding. Well, we know that the left part is quite simple, right? In each decoding step, we only leverage an efficient draft model like Llama 7 billion compared to the Llama 70 billion. And given the input prompt or the prefix, the draft model starts to draft iteratively, autoregressively, or non-autoregressively. Anyway, it's an efficient, very efficient process, and it can give us a multiple draft tokens as the speculations. And then we illustrate how the target large language model could verify all these draft tokens in parallel in a single decoding step. Okay, like in this picture, we can see that the draft tokens this is good, the 4 draft tokens, right? The yellow ones. And the green part is a prefix, the BOS token as the input prompt. And the original target large language model output would be, this is good news, right? Contains these 4 tokens. And in the first step, we can see that given the input prompt BOS, the target large language model will generate a token based on this prefix, like this. This is, corresponds with the autoregressive decoding process of the target large language model. And then we obtain this verified token, this in the gray part, and we directly compare this token, this verified token, with this draft token. And if they are exactly the same, if they are equal, we can see that the first draft token, it passes the verification. And then we can get to the second draft token. In the verification of the second draft token, we can assume that all previous draft tokens are correct. The blue ones, we assume that they are correct tokens. We assume that they pass the verification so that they can input into the target large language model the BOS token and the token this. Well, given these 2 tokens, the target large language model will generate the second token is, and then we compare this verified token with the draft token. And obviously they are exactly the same. So we say that the second draft token, it passes the verification. And this process will continue until we find a position or a draft token that it fails the verification process, like the first draft token. Well, we assume that the first 3 draft tokens are correct. This is good, right? And given BOS token, and this is good, the target large language model will generate its own output, its original output, news. And the news token, the token news is not the same to the draft token good. So we say that the first draft token, it fails the verification, and we call this position the bifurcation position. The bifurcation position means that the index of the first draft token that fails the verification process. And once we find a draft token that fails the verification, the assumption is not correct, right? We cannot assume that all previous draft tokens, they are correct. They will pass the verification process, so that the subsequent tokens, we will discard all of them. And actually, this process can be processed in parallel based on the teacher forcing process or the teacher forcing strategy during the pre-training stage of the large language model. And when verifying each draft token, we can always assume that its previous draft tokens are correct. And then we directly compare the original output of the target large language model, the verified tokens, with the draft tokens. And all 4 draft tokens can be verified in parallel in a single fold pass of the target large language model. And once we find a verification position that fails the verification, we discard all subsequent tokens. And if we have more draft tokens here, we all discard them because the assumption is not correct. And we cannot directly use the verified token on the subsequent positions. And in this example, we have 4 draft tokens, right? And we got 3 draft tokens that pass the verification. And given the prefix BOS token, and this is good, the target large language model will generate its original token, like the fourth token news. And news can be seen as a correction of the first draft token, the bifurcation position, right? It means that during the draft process, the draft model guesses correctly on the future 3 decoding steps of the target large language model. And on the first position, on the first token, it fails. And the large language model corrects its token by, and all this process just conducts in parallel. Okay, so speculative decoding facilitates multiple tokens to be decoded in a single target large language model forward or decoding step. And here is a latency comparison of speculative decoding to autoregressive decoding. Well, we can see that in this case, speculative decoding is faster 2 times than autoregressive decoding. And we can see that the draft process is very efficient, and the verification process just is conducted in parallel. And here is an example from Medusa, a widely used speculative decoding method from their website. We can see that when generating the same output, Medusa exhibits faster speed than autoregressive decoding. And we can see that their outputs are exactly the same, and the only difference is the decoding speed. Okay, so now we provide a formal definition of speculative decoding. Speculative decoding is a draft then verify decoding paradigm in which at each decoding step, it first efficiently drafts multiple future tokens as speculations of future decoding steps of the target large language model, and then it verifies all these draft tokens in parallel using the target large language model so that we can speed up the whole inference process. And here is a timeline of speculative decoding from our survey paper. And we can see that the concept of speculative decoding is proposed in 2022. And after this year, many researchers draw interest in this promising research area. And we are very excited to see that there are more than 140 papers published in 2024, the last year. And we are also very excited to see that speculative decoding has been supported in multiple inference frameworks like Hugging Face transformers, PyTorch, and the VLLM. And in these inference frameworks, we can experience the speed up of speculative decoding within a few command lines. And speculative decoding has also been supported in pre-trained large language models, like in the Facebook Meta paper and the DeepSeek version 3. And in these papers, they investigate to embed the speculative decoding capability into the pre-trained stage so that the model can leverage this capability during the inference process. And here comes the overview of this tutorial. And we just finished the part 1, the introduction and definition of speculative decoding. And then we are going to introduce the history and a taxonomy of widely used methods in speculative decoding. And the next is the Q&A and coffee break for 30 minutes. And after, we're going to introduce some cutting-edge algorithms in this area, the downstream adaptations, and final remarks. Okay, thank you, and I will pass it on to my colleague Chen.
Hey, hello everyone. My name is Chen and I'm from TikTok. I'm very honored to be here to present a talk to me or message for speculative decoding. Okay, so first let's talk about the history of speculative decoding. Uh, as you can see in the timeline, the first time the black-white decoding has established a framework for speculative decoding, first in 2018. And then there appears the method aggressive decoding in 2021. And then in 2023, the speculative decoding and speculative sampling. There are some concurrent works, both all propose the same concept and has established the foundation of speculative decoding. And after that, the area has grown a lot and raised a lot of interest from industry and also academic. And the speculative decoding was formally introduced in 2023 as a general decoding paradigm to accelerate language model inference. So let's recap the core idea behind speculative decoding. So in the left, you can see the autoregressive decoding. At each step, the model decode one token. And at the right, first we will leverage an efficient drafter to draft some tokens, then use the original model to verify in parallel. And if the first, when it meets the first unused token marked as a gray, it will generate its own predicted token. And then we will iterative the pipeline for several times to save compute. And so let's talk about the first framework, like to establish the basic concept for speculative decoding, the block-wise decoding. So it's proposed by Google in 2018. And the first step is to draft, as you can see in the framework. So the first step of block-wise decoding is to use different proposal models to draft multiple tokens in parallel. So here we show, sorry. Here we show the different proposal models. The first to parallel predict the next and the following and the subsequent tokens in parallel. And then we use the original model to verify these different tokens. Okay, here we use the original model to verify, and these are also executed in parallel. And we can see here the first two tokens, DIN and the, are accepted by the model, but for the car token, it is rejected by the model. And then after the accepting, the sentence will be decoded as I saw a dog rat in the, and then it will iterate this procedure to generate more tokens. Okay, so because the block-wise decoding has employed different proposal models to predict tokens in different positions, you can imagine that you want to, in parallel, generate the next token, next, and the subsequent token in the same time. So here it add some more language model heads to the original transformer architecture to parallel draft across positions. Just as this is our original decoder output. Usually we directly feed this original decoder output to a language model head to predict the next token. But here it leverage two actual heads to in parallel predict the next and the subsequent token. Okay, so I think you will imagine that why block-wise decoding can be so fast. So it bring some negative impact on the performance? Actually, no, because in theory, the performance of block-wise decoding is equivalent to greedy decoding. Why? So because of the verification guarantees the same output. It's just like you you still use the original model to verify if the draft token is the top one candidate by the model. Here we can see the experimental results compared to the transformer base use beam size as 1. The blockwise decoding shares the same results, experimental results, but it can achieve some speed up, like at most twice. So actually, the speed up factor today for speculative decoding is also around 2 or more. But originally, the speed up at most twice is still not very significant performance improvement because researchers want to find more efficient ways to accelerate the inference. So, and when it comes to 2023, there is a concept of speculative decoding, the formal definition. So we can see from the blockwise decoding, it shares most of the model parameters from your target model because it's just added to actual heads on top of the original transformer model. So I think for the follow-up works, most of them try to improve the model by separating the draft model from the target model. So then the draft model has an independent parameters, which guarantee the model's capacity. So here is the most important conclusion that the drafter model should be seriously invested to guarantee its capacity of accurate drafting. If it does not do accurate drafting, then the draft tokens will have a lower acceptance risk than speculative decoding will have a relatively small speed up. Okay, we can see from the results of the first one of the first paper about speculative decoding, then similar results, but using speculative decoding, using a separate drafter, will have a much better speed up on the same tasks. So you will be curious that what is speculative decoding? So where is the name? So the name of speculative decoding is from the speculative execution, which is an optimization technique used in computer science. It is to say a system performs some tasks in advance to avoid delays that would have to be incurred by doing the task after it is known that it is required. So usually we see it is speculative decoding, and the term is accepted by the community now. Okay, so we have talked about speculative decoding. So for decoding, we usually refer to greedy decoding. It means that your model outputs the token with the largest probability every step. So for our counted language models, we usually want it to be sampled. So the sample means for every step, you can randomly sample a token from the most probable tokens. We have a comparison here. The left is greedy decoding. At every step, you just use the top one. But for sampling, you may choose one from top 3 or using some criteria to filter out impossible tokens and random select one. And our online service, like a chatbot service, usually use sampling. But for some like professional tasks, they usually use greedy decoding. For sampling, it has another benefit that every time you chat with a chatbot, if you use the same request like hello, how are you? It will always have a different response at every time. It's because of the sampling. So for greedy decoding, speculative decoding generates the same output. So how about for sampling? So researchers also propose the speculative sampling. It will be more complex than the decoding because it will maintain the output distribution. It will have the same output distribution instead of just the only one exact output. So usually the procedure is that First, the generate the draft token X. Here we assume it's just a one token, but it can be also extended to multiple tokens. And then we get the probability of Q as a draft token from the prior target model, and get the probability P as the probability of generate X based on the prior draft model. So this can be executed in parallel. So after that, we compare the value of Qx and Px. If Qx is larger or equivalent to Px, then we accept the token. So the complex scenario occurs when the Qx is not larger than Px. So we will reject the model, reject the token according to a probability. So it means that you will have a chance to reject the token, but also you have a chance to accept the token. So if it is rejected, we will resample a token from a designed distribution instead of the original draft distribution or target distribution. So it's a relatively complex, but it is verified in theory. It shares the same output distribution as the original model. So this is a speculative sampling. And speculative sampling can be used with different sampling techniques because they can be all cast into sampling from an adjusted distribution. So if you are familiar with sampling techniques, we have top K, select token from the best K candidates, and top P, also known as nuclear sampling, select a token from candidates whose cumulative probability is larger than P, and also temperature. A greater temperature means diverse, more creative and more diverse results. Okay, so after the formal concept of speculative decoding and the speculative sampling, we currently have the spec bench, a benchmark for speculative decoding. So from the benchmark, you can see different methods have different advantage, but the eco method achieves the highest speed up rate, ranging from 1.8 to 2.4 across most subtasks. But here are also some special tasks like summarization. Some method will have a much better speed up on summarization. So this kind of methods are designed for this special task to accelerate. So we can see different methods have different advantage in different scenarios. So you should choose one suitable for your task if you want to use speculative decoding. Okay, so after the brief history, I want to share the taxonomy of speculative decoding. So we can see the two parts. The first part is drafting, and the second part is verification. They are both important. So usually, different methods have different drafting techniques more, and they can be split into two categories. So for the drafting process, it is very important for the speed up. So why? Because we have two crucial factors. The first is speculation accuracy. So how many draft tokens are accepted by the verifier? So if a draft token, you just generate 10 tokens and 10 tokens are all accepted once by the verifier. So it can accelerate the inference a lot. But if you generate 10 tokens, just one of them is accepted by the model. So it does not bring a lot of speed up. So then we must consider the drafting latency because the draft model is still a model. So it still costs some effort to generate the draft tokens. So that's a balance. We want to decrease the drafting latency and also increase the speculation accuracy. So the best method should be in the green area. So we have introduced two drafting strategies. The first is independent drafting. So you can see the meaning from the name independent drafting. Independent drafting leverage another model, a draft model, to help the target model. So here we have to different choices. The first is how can we select the draft model? And second, shall we tune the draft model? Okay, let's get started from the first independent drafting. And for the independent drafting, the first independent drafting is also proposed in the first speculative decoding work. It leverages a non-autoregressive language model. So let's show again about how autoregressive language model works in decoding. So we can see first we have a prefix build fitted to the model, and it will generate large. And then one by one, we can have the large feed into the model to generate language. And one by one, we have 4 steps to generate the whole sentence, build a large language model. So this is the autoregressive model. So what about non-autoregressive? Non-autoregressive means it's in parallel. So first, usually we just feed the build to the autoregressive model, but here if we already fix the target length, like we know how many tokens we will generate in prior, so we can build feed the build and some mask tokens into the model, and the model can decode them in parallel to directly generate the whole sentence. So after one step, you can generate the whole sentence, build a large language model. So it's like a magic because non-autoregressive model does not interact with each other at each step. It just feeds some mask tokens and predicts them in parallel. So compared with an autoregressive model, autoregressive model is relatively slow because non-autoregressive does not have this kind of feed and just in parallel to predict the whole sentence. But now autoregressive usually does not give good quality on the output. But here, if we use it for the draft model, it will be very suitable because the draft model is just try to generate draft tokens. Then the draft tokens will be verified by the original model, so it does not hurt the performance. So non-autoregressive model is very suitable for generate draft. So you can see a real case from the original paper. Since non-autoregressive models decode multiple tokens in parallel, so they can be good draft models. Here we see giving the prefix millions of, and the decoder directly decodes the whole sentence here. Okay, so what's the drawback of non-autoregressive model? We have just mentioned non-autoregressive model is usually does not give the equivalent quality as autoregressive model, but they are suitable for draft model. So due to the fact that current language models are almost autoregressive, so you have to train a good non-autoregressive model to match the generation quality of the autoregressive model to become a very efficient drafter. It becomes unfeasible current days. So can we have a model which is much faster but still autoregressive? That's a core point of the follow-up works. Like we can use small language models. So due to the ability to generate subsequent sequences quickly, so small language models also serve as ideal draft models for larger language models. Here we can see first the small models generate several tokens. Usually we have a hyperparameter to generate how many tokens in prior. And after the drafting, and the large models verify them. So because small models usually have smaller parameters, so the decoding will be fast than the large models. Okay, so it is also, this kind of technique is also employed in the first 2 speculative decoding papers, and also a Hugging Face blog, assistant generation. Okay, so we have mentioned that small language models are very good for the drafting. So there is a trade-off. So because between the size of the draft model and the acceptance rate, as we shown in the drafting, this is a trade-off. So if we use a target model as a T5XXL, it's a 11 billion model. So we can use different draft models as a draft model for the target model. Here you can see the most speed up is achieved by the smallest model T5 small, and the acceptance rate is not very high compared to other larger models, but it is very fast. So consider the drafting latency, it achieves the most speed up. So usually there is a trade-off because you cannot get if you have a lower acceptance rate, you may use a larger model to achieve better speed up. Okay, so usually to improve the draft quality, we will train the draft model, or we will align the draft model's output with the target model. So here, sequence level knowledge distribution is always applied to align outputs of drafter with those of the target model. So the idea is very simple. For a target model, like something we say, hello, how are you? And the target model give different response. And we use this as a paired data to train the drafter model. That's a core idea behind it. So first we use the target model to generate tons of sentences, and we use these sentences to train the draft model to align the distribution with the target model. It's also a very common technical in current speculative decoding and proposed in 2016. So after this kind of knowledge, sequence level knowledge distribution, we still face a problem that if we do not have a small language model. So this is a limitation of our model-based, independent drafting model-based methods. Both the non-autoregressive language models and small language models should have the exactly same tokenizer with the target model. If you know the model of Queen, you know that for Queen, the smallest Queen model does not have a same tokenizer as Llama. So the Queen model can be used as a draft model for a larger Queen model, but it cannot be used for Llama. That's a problem. So usually if you have the computing resource to train a very large model, and you have to train a paired, really small model, but very powerful model to accelerate the speed, the inference. So given these limitations, we can also design some non-model based independent drafting methods. So the first classical method is context retrieval. It's also very simple. So given your prefix like after lambda, num, this is a code, and we can use it to retrieve from your corpus. And here we just use exact match using the suffix, and we can retrieve from the corpus as different continuations. And then we can do the try tree and try to build it. The build process is very simple. First, we do some statistics on the, like here we statistics that the first token is always in, and the frequency is 5. In fact, it appears 5 times. And we build the first node from the root node, and this is in. And following the procedure, we can have the try of the continuation. And after the building the whole try tree, we can finally select most frequent nodes to build the tree-based draft. It means that we ignore this kind of nodes because they appears very infrequently and may not be accepted by the verifier. So we just keep this subtree as a draft tree. We will later introduce a draft tree-based verification, but here it can also be kept as a draft chain. Like you can choose the most frequent chain, and this is a normal draft token like in, range, and left bracket. Okay, So this is a context retrieval. You can see by building the draft, it does not require any model. Here you just use a prefix to do exact match based on your retrieved corpus and build the trial. And context retrieval is very simple and easy, but there is a more easier method if you have some special tasks. For some tasks, your input and output have high similarities. We can also use part of the input as an effective draft. This is also very interesting idea. Here we show example task of like given question over a knowledge base. Here are two dogs, and we want to use the model to answer the question. This kind of pieces are directly copied from the documents. So you can see the answer have a large overlap with your input for the model. So we can also use the part of the input as an effective draft. Here we show the first giving the documents and the question. The model has decoded to comes, and then, okay, here's the first token comes input to the autoregressive decoding model, and then we comes from because comes predicts from, and we have the from, and then we have the token also decoded by autoregressive decoding. After this, we can see comes from the have matched the in part of the input, the prefix, and we can directly copy the follow-up tokens from the input. This is a pancreases, cows, or pigs. We can, because it matches the prefix from the, and we can directly copy the remaining as draft. And we feed this draft into the autoregressive decoding as verifier because it is in parallel. It can verify these draft tokens in parallel. And we accept all of these tokens and it accelerates the decoding. So if we accept the draft tokens from copied from input, then it directly decodes pancreases of cows here in one step. Okay, so this is a basic idea of copy as a draft. It's suitable for some tasks like editing. You want to edit passage, or usually some like fix some grammar errors, and also if you want to reuse some of your multi-turn conversation. Okay, so this is a part of independent drafting. We can see a lot of different methods proposing different interesting idea. And also next, we will introduce a self-drafting paradigm. As we have already mentioned, independent drafting requires an independent model, which must share the same tokenizer as the target model. So usually we cannot achieve this because we do not have the computing resource to train another small but powerful draft model. So here we can use the model itself as a draft. So for the self-drafting, we usually have three classical technicals. Here are the actual head, layer scaling, and mask predict. Okay, let's talk about the self-drafting models. So the first is the actual head. It has already been explored in the pioneer, the block-wise decoding method. Like it uses the target model parameters and use some extra heads to predict the subsequent and the subsequent tokens in parallel using different heads. Here we can see it builds extra heads on top of the draft, on top of the target model to generate the draft. And also this kind of idea is extended to the popular work Medusa. Medusa also leverage extra heads based on the transformer layers to generate different subsequent tokens. Here, the first head predicts the next token, and the second head predicts the next token, and the third head predicts the following one in parallel. So yes, you can see that different ideas can work in different scenarios and in different areas. First, the blockwise decoding is proposed in 2018, but the speed up is not very efficient. But for now, the Mendoza has achieved a good speed up using the same principle. Okay, the second category of self-drafting is layer scaping. We can focus on this part. During the drafting stage, the language model selectively scapes some of the intermediate layers directly to generate the draft tokens. And this is a verification phase. And it's first introduced in the draft and verify paper. So we should be curious which layers to scape, because there are so many layers. We can scape maybe every layer, then you cannot generate every meaningful token. So here, the author of draft and verify use a black box evaluation function and Bayesian optimization to optimize layer selection. So it models the layer selection as for each layer, one binary vector corresponding to whether to scape this layer. And in default, each one should be one. And then we can use the Bayesian optimization to evaluate the inference time per token and also the acceptance rate. And after this, we can use this acceptance rate as a metric to optimize the vector here. Because it is a non-gradient based, so it requires a black box evaluation and optimization technical to get which layers are selected during the inference. Okay, so this is a layer scaping technology. And the last self-drafting technical is mask predict. Actually, we have already introduced the non-autoregressive language model, right? So the non-autoregressive language model can decode the wholesomeness for one pass and use parallel decoding. But it is trained also using the non-autoregressive object. It's a different object. But for this work from accelerating transformer inference for translation while parallel decoding in 2023, this paper used a mask predict method on top of an autoregressive language model. It demonstrates that even for an autoregressive language model, you can still do parallel decoding. You can see this is just as similar as the tokens feed to the non-autoregressive model. And here we feed build as the only prefix and some padding tokens. Padding tokens do not have any meaning, just some like a placeholder to indicate that model, hey, here is a token you should to generate. And we feed these tokens into the autoregressive language model, and it can generate next token for each token. Okay, so after this iteration, usually the results are not so good because autoregressive language model is trained to decode a token step by step. So here we have to iterate k iterations for parallel decoding. So after k iterations, every time the token updates will Jacob methods. It's like an optimization methods, and you can find more theories in the paper, but it usually can converge. And after each iteration, if it converges, you can directly get the final output large language model. So the 3 pair tokens are filled with large language model. So this is a self-drafting mask predict method. So it's built on the autoregressive language model and use some optimization, numerical optimization methods to turn an autoregressive language model to iterative non-autoregressive decoding. So this is also a very promising method for the self-drafting. Okay, so after this, we have introduced these 2 different drafting methods. The first is independent drafting, and the second is self-drafting. So next, we will talk about the verification. So usually the verification is also very important because it determines the output quality. Because draft tokens can be accepted or can be rejected. It depends on the verification. So usually we verify the different draft tokens in parallel using the original model. So the first, we care about the verification quality. So it's a lossless or approximation as the original. If it's approximation, it can yield more speed up, but usually decrease, give some negative benefit, negative impact on the output quality. So also we have the verification support. We have already mentioned the graded decoding, sampling, and last we will introduce the token tree verification. So the first, we care about the verification quality. We have introduced in the first the blockwise decoding method. So for the graded decoding, if you have a target model, the first top one tokens in different steps. The first step is we, and the second step is live. So this is graded decoding results of the target model. So for draft tokens, it means if you draft we live, it is accepted by the model. But if you draft we love or he live, it does not. It will not be accepted by the the target model. So this is lossless because we guarantee the unique output, and it should be equivalent to the gradient decoding result of the target model. So this is a strict matching. You have to match the results, then you can be accepted. So this is a lossless, and usually it yields the exactly same result as the target model. So what is approximation? Usually we have some relaxed criteria to verify the draft tokens. Here we relax the top one result to top three candidates. For example, here we have the first step, we can choose either from we, he, she. In the second step, we can choose from live, love, wrong. And so in this case, if the draft tokens are still the three groups, they are all accepted by the verifier. But it will have a slightly different distribution as a target model. So it's relaxed, but have a better speed up, but have relatively lower output quality. So then we have, actually we have a lot of relaxing methods. Here we just demonstrate the most simple one, relax the top one candidate to top K. You can choose more candidate methods to try to not decrease the performance a lot, but increase the speed up. The last one we want to introduce is verification support. It's very important because we want the model or the method to support different sampling method or different verification. And the first support is graded decoding. It's very simple. Here we draft tokens build large language action doing. It's not very fluent because it's generated by the drafted model. And the target model do verification in parallel and accept the first tokens because they are also the top one candidate by the target model. But it rejects action and doing because they are not the top one candidate by the model. But how can we leverage the model itself? Because you know that in this case, the result is the model already sees the prefix large language. So the target model already can give the correct token by itself. So this is the correct token model. So finally, we can see, given these draft tokens, the model accepts two tokens by the draft model, and it generates another token following the draft tokens. So here we have three tokens in one time. So this is how we leverage the target model itself to benefit. So in this case, we can see draft usually when the acceptance rate is fair, larger, like larger than 50%, then speculative decoding always gives the speed up because here we also reuse the prediction by the target model itself. So at each step, at least the model can decode one token. And this is a greedy decoding. And also we can see the model token is provided by the target model, and the large language is verified tokens accepted by the model but provided by draft model. So if in the case of sampling, if the draft token still build a large space model too, and this will be judged, verified by the target model also in parallel. But the criteria is relatively complex, as we previously showed. It's not just one just a simple try if it is the top one, because the output distribution should match the original distribution instead of just a concrete case. So here, if the model accepts the first token but rejects the second token, and then it also accepts the last two tokens. So what will things going on? Here we can see, okay, so the first valid verified token is large. So even these two tokens can be accepted, but because the previous token space cannot be accepted, so these two tokens are also dropped because we use an autoregressive to decode. And then the model can also resample a token like a multimodal. So here if we trans tokens into sentence, it's build a large multimodal. So it's not the top one, but it's a sampling result, so it's reasonable. And the verified tokens are provided by draft token is only the first token. And the resample tokens are provided by the target model itself by sampling on an adjusted distribution. Okay, the last one is a tree token verification. It's relatively complex. If you remember the try we have seen in the REST work, and it tries to build a tree instead of a chain for the drafting. So it merges multiple candidate draft sequences into a token tree with shared prefix. Here we mean shared prefix. Here we finally keep the I am very and I like these two candidates. And if we realize them on the attention mask, it will be such kind of thing. So this tree can be used for parallel verification. It may be a little bit hard to understand, but we can split this tree into two candidate drafts. So the first one is I like. You can see these three red. Okay, so these three red can be composed into the causal mask, just as the GPT used. And another draft is I am very. So you can see this also a causal longer mask. So you can split the original mask into two, but they share the same prefix. That's the core idea behind tree token verification. So in this case, because they share the same prefix and relatively independent in the following tokens, so the model can use once to verify these two drafts in parallel. So it can accelerate the speed, the inference speed also. Okay, so here we have introduced the history of speculative decoding from the blockwise decoding. It serves as a foundation framework of the speculative decoding. And then we introduce the speculative decoding technicals and also speculative sampling. They can be used for both greedy decoding, sampling approach, and theoretically, it does not change the output distribution. So this is the most promising part by speculative decoding. The last one is that we introduce the taxonomy of different drafting methods and verification methods. And the drafting methods include independent drafting and self-drafting. And the verification encompasses both verification quality and verification spot. Okay, so I have finished my part, and next we'll we will have the Q&A session.
Okay, so do you have any questions?
I'm from Japan. So I have one question. I think you talk about some non-regressive model using as drafting or maybe use small model. So I wonder whether the quality of the small model matters for the whole performance or latency.
You mean the comparison of a non-autoregressive model and a small model?
For example, you compare different drafting model.
Yes.
Non-autoregressive small model.
Yes.
So does the quality of that drafting model matter?
Yes.
On the overall performance?
You mean the overall performance after speculative decoding?
Yeah. For example, like comparing.
Yes, they should be same as the original target model if you use greedy decoding, because drafting can be rejected. Imagine that you draft many tokens, but all rejected by the target model, and it can generate token one by one. So it is equivalent to the original target model output if you use greedy decoding. So even for non-autoregressive language model or small language model.
Which means that if you have a good verification model, you still have a good.
Yes, we usually the verification model is just the original model. Like you want to accelerate Llama 70 billion, you use the Llama 70 billion to as a verification model.
Thank you.
Thank you.
Okay, so if there are no more questions, we can get to the coffee break and we get back at let's see, 11 o'clock.
Yeah, 11. Okay. Thank you.
Thank you, guys. Okay, first let's recap the basic paradigm of speculative decoding. Well, the entire inference process of speculative decoding, it involves the collaboration of two models, right? The draft model, which is efficient, and the small one, and the target large language model, which is the model that we would like to accelerate. And during each decoding step, we first obtain a few draft tokens through the efficient draft model, the smaller one, and then we use the large language model, the target large language model, to verify all the draft tokens in parallel. And once we find a draft token that fails the verification, we discard all subsequent tokens. In this way, we can ensure that the tokens that pass the verification, they're exactly the same to the original output of the target large language model. Okay, and here is the definition of speculative decoding. Well, speculative decoding is a draft then verify decoding paradigm. It means that in a decoding process, if two models or a draft module is applied in the decoding process, if a decoding strategy, it follows the draft and then verify this decoding paradigm, we see it as a part of speculative decoding. And in each decoding step, this paradigm first efficiently drafts multiple future tokens, the draft tokens, as guess or speculations on the future decoding steps of the target large language model. And then we use the target large language model, the original one, to verify all the drafts or the guesses in parallel so that the original output will not be changed. Okay, and considering this paradigm, we would like to note that the ultimate goal of speculative decoding, our final aim is to accelerate the inference, right? The overall efficiency of this paradigm. So this is the goal that we should always keep in mind. To achieve this, we aim for a high speculation accuracy, right? We would like more tokens to pass the verification so that we can get more parallelism in each decoding step. For example, if we get 10 tokens past the verification and we ignore the drafting accuracy, we ignore the drafting latency, it means that we can get 4 tokens decoded in a single decoding step. And ideally, it means that we accelerate the inference process by 10 times. And however, we should consider the drafting latency, right? Because the more intuitively or typically, if we get higher speculation accuracy, we need a stronger draft model so that the drafting latency will be higher. For example, we increase the draft model size, we add more parameters, and we conduct a more complex drafting process. So in recent works, people have tried a lot of strategies to investigate the model scales of the draft model, the drafting architectures, and some researchers have investigated a strategy called efficient drafting. And when we say efficient drafting, we mean that we do not alter the original model scale or the architecture of the drafting model. We just propose some efficient strategies to get more tokens past the verification. Okay, and in the first part of this, we would like to introduce some efficient drafting strategies. The core idea behind this is how to leverage our context to accelerate the inference process to help the speculative decoding. And before the introduction, we will first recap some state-of-the-art speculative decoding algorithms. And the famous one is Medusa, right? We introduced it before in part 2. And the left part is the original large language model, right? It contains the embedding layer, a few decoder layers, transformer layers, and lastly, we get a language modeling head. It translates the representation from the last hidden layer into some semantic tokens. And Medusa just some language modeling heads, the extra language modeling heads compared to the original one. And so that in addition to the original token that we would like to generate in the original large language model, we can decode more tokens, like 3 tokens in this example, by inserting more language modeling head, right? And these language modeling heads, they contain very few parameters. They are just feed-forward networks. They are equal to the original language modeling head. And the advantage is that this Medusa head, the language modeling head, they can utilize the computed representation from the last hidden state. And so this is a very good accuracy latency trade-off, right? And the core idea behind it is we reuse the computed representation of the original large language model. We leverage the original language model to conduct the most of the computations and only separate it to the to the final layer of the decoder transformers layer. And by fine-tuning this Medusa head, we can get very good speculation accuracy, and the latency is quite small because the most computations is performed by the original large language model. However, Medusa have some drawbacks or weaknesses. We can see that if we have the representation from the last layer, except for the original language modeling head, we have some few Medusa head to produce actual tokens, draft tokens in parallel. However, the draft tokens could not see each other, right? They do not have explicit dependency between each other. So it is more like a non-autoregressive way to produce these draft tokens. It means that the speculation accuracy may be not optimal that as we think. And the next work, Ego, we can see it as the current state-of-the-art method in speculative decoding. It tackles this challenge, the dependency of the draft tokens, by introducing an autoregressive, you can see it like a language modeling head, because if we obtain the original representation from the last few layers of the original language model, we can use an autoregressive model, well, iteratively to generate the draft tokens. So that compared to Medusa, compared to the non-autoregressive draft way, Ego introduced token dependency between the draft tokens so that it can further improve the draft quality, so as the speculation accuracy. And if we get the last representation, we get some words. It's the draft model contains an embedding layer, an autoregressive hide, a language modeling hide, and by conducting some iterations, we can obtain a few draft models. And this is a drafting process. And if we get the draft tokens, we input it into the original large language model, and the original large language model verify all the draft tokens in parallel, as we just mentioned. Okay, so after introducing the currently thought methods like Medusa and Ego, we could see that even these models, they obtain an quite optimal accuracy latency trade-off. However, their drafting latency could not be ignored, right? They still got a draft module, whether non-autoregressive or autoregressive, they still contain some parameters, and we could say that they are still not that efficiency. And in this table, Ego is the current state-of-the-art method in our spec bench, the evaluation benchmark of speculative decoding. We can see that it achieves the best speedups across most scenarios, except for the summarization. Because in the summarization scenario, the input and output, they have high similarity, and some text spans could be directly copied from the input to the output. So the PLD is the current best method because it just copies input from the output. It do not introduce extra drafting latency, and the speculation accuracy is quite well because the scenario is very specific and the input output has some inherent similarity. But in most scenarios, Ego is the best method, and it is very general method for language generation. And by saying that, we could see that even Medusa and Ego, they have some parameters. They have that kind of drafting latency that we cannot ignore. And we just introduced the copy-based method that they are quite efficient. They do not introduce extra efficiency. So we should ask that, is there a more efficient way to draft so that we can push forward the boundary of the accuracy latency trade-off? And as we just introduced in part 2, copy is a very efficient method, right? But it's limited in a few application scenarios, such as retrieval augmented generation. In this scenario, we aim to retrieve some spans, some materials directly from the input material, like the document or the paragraph. And if we find some spans that are exactly what we want to say, we can just copy them from the input to the output. And they are very likely to pass the verification since they're just what we want to say in this scenario. We just retrieve some contexts from the input. And in other scenarios, such as cache assistant dialogue and multi-turn conversation, we can also find some input that has a high similarity between the output. And in these scenarios, we do not need an extra drafting module. We just copy the text spans from the input to the output if we find some matched prefix. And this scenario, this kind of method, the copy-based method, have been implemented in a very famous PLD, the method that we just mentioned, the open source GitHub repository, and it receives a lot of research interest and has been used in a lot of inference framework like VLM and Hugging Face transformers. Well, even though this method is quite simple, right? But it is very easy to implement, and the method behind it is quite easy to understand. So it is a very famous method in speculative decoding. However, as we just mentioned, this method is limited in specific scenarios, and in some kind of scenarios, like general generation, we could not find similar spans or matched spans from the input, right? Like translation, we have two kind of different language, so that we could not match the spans from the input to the output. And in these scenarios, the copy-based drafting is quite limited. It has a relatively low speculation accuracy. So is there a more general way to obtain context drafts efficiently? And as we introduced by my colleague Chen in part 2, we have RIST, right? The retrieval-based speculation decoding. Well, PLD or the copy-based methods we just introduced, they copy the text spans from the input prompt. However, in most scenarios, we do not have a input prompt that is such long, right? So we should increase the corpus or the context that we could utilize. And the rest they just build a large corpus from some training data or from open source corpus. And if we get this corpora, we just do some retrieval and we find some matched prefix from the retrieval corpus, and then we can directly utilize them as a draft. So in this way, the drafting latency in this process is the retrieval latency, right? Because you do not have extra parameters. You do not need to do drafting, decoding, you just do retrieval. And in the most recent work, SAM decoding, compared to the previous retrieval-based method, it introduced the suffix automation to do the retrieval task. It just use the suffix automation to find the matched prefix very efficiently and use these drafts as the input to the original large language model. And very interestingly, we find that these kind of efficiently context-based or copy-based methods, they can be combined with the SOTA state of the art method like equal2. And if the two very strong methods are combined, the efficiency could be further increased. And we can see that by combining SAM decoding, the context-based retrieval, the equal2 speed up is further increased in our evaluation benchmark from 2.38 to 2.58. Well, combining these methods bring up to 10% speed up improvements. And this gives us quite exciting research insights. The first insight is that a single drafting method may not achieve an optimal accuracy latency trade-off, because we know some methods like Eagle and Medusa, they have extra draft parameters. They may be accurate, they may have high speculation accuracy, but they may not be efficient enough. And the copy-based methods, they have very efficient drafting process, but the speculation accuracy of these kind of methods may be low in some specific scenarios. However, if we combine these methods, like simply speaking, if we set a threshold to switch between both methods, we can find the optimal scenario to apply a specific method to achieve higher speedups. Okay, and the second benefit is the collaboration between different drafting methods brings extra benefits. By adaptively switching between these methods, the accuracy latency trade-off would be further enhanced. However, we should keep in mind that if you are hosting a service system, you should consider the service complexity of the system. So if the drafting methods are very complex, if it contains or requires switches between different methods, maybe the complexity of your service system will be further increased. However, if you just aim for higher speed up, if you do not care about the complexity, maybe you can try to collaborate between different drafting methods. Okay, and then we can, the next part is verification. And if we consider the verification, we should also consider the verification efficiency during this process. And as we previously mentioned, the key in the verification stage is to verify as many tokens as possible, right? Because if you can increase the capacity of the verification process, if you verify as many tokens as possible in parallel, maybe you can increase the tokens that pass the verification, right? However, you should also consider the verification latency, right? It is also considered in the overall latency and will influence the overall efficiency of the system. And so the key question is that we are given a limit of verification length. It means that we can only select a fixed length, a fixed number of draft tokens to do the verification, to perform the verification process. Because in this scenario, we verify 4 draft tokens, right? And even though this process is conducted in parallel, and if you increase this draft length to 100 draft tokens or 1,000 draft tokens, the verification latency will also increase largely. So we should always consider a fixed length of draft tokens like 64 in Medusa or Eagle. And the question is, given the limit of verification length, an important research question is that we should select high quality draft tokens to put into the original language model to conduct the verification process. Or in other words, we should filter out low quality drafts, because in this scenario, we do not much care about the drafting quality, right? We just obtain a set of draft tokens. And in this process, we should consider which draft tokens they are high quality and which part of draft tokens is of low quality. So in the next part, we will introduce the dynamic tree verification. We will discuss how to select high quality draft tokens to conduct the verification process. Okay, and let's first recap the draft tree attention. It has just introduced in the part 2, right? The Medusa implemented a very simple and intuitive implementation of this tree attention. Compared to the previous methods such as speculative decoding, right? They just verify a single sequence of draft tokens, and they do not have the options between different sequences. And if we conduct a tree mask, we can verify different draft sequences in parallel, and this is implemented by applying a tree mask. And when applying this tree mask, as my colleague Chen just introduced, we can verify a specific sequence of draft tokens, and we conduct the specific attention mechanism like the autoregressive decoding, and so that we can get more options or more sequences to be verified. And this is a static draft tree architecture in Medusa. In this architecture, this architecture is fixed during the decoding process. It means that whatever context that you got, you just apply this static draft tree and like the root node and the leaf node, the whole architecture, they are fixed. It means that in this draft tree, we can see that the models pays more attention on the top one predictions. It always the top one predictions because the top one predictions have the largest confidence, right? And they are more likely to be accepted. So we should allocate more capacity to its subsequent tokens. So the top one predictions has more subsequent leaves, and the top K tokens like top 10 here, we just verify the tokens of layer 1, and in subsequent layers we discard all tokens because the top 10 token here has a relatively low possibility to be accepted. So we do not allocate more computer resources to verify the subsequent tokens. So the static draft tree is built upon a strong assumption that, like we just mentioned, the acceptance rate of a draft token depends only on its position in the tree or in the top K prediction, right? If it is a top 1 prediction, we investigate it more on its subsequent tokens. And if it's the top 10 prediction, we just verify itself and do not explore more. And however, is this assumption enough? And in the paper of Eagle2, the author investigated and visualizes the acceptance rate from different positions. And if we are given a query and we consider different positions of tokens, like layer 1 means that the top K predictions of the first draft token, and layer 2 means the top K predictions of the second draft token, right? So the P1 position means the top 1 prediction of the top one of the first draft token, and the P2 means the top 2 prediction, the second prediction with the second largest possibility of the first draft token. So intuitively, we can see that P1 and P3 they have higher possibility to be accepted, right? Because the draft model has a high confidence of them. They are top 1 predictions, and the P6 and P2 they have relatively lower possibility to get accepted. And in this visualization, we can see that it is indeed the like what we just said, and the position, the P1, they have relatively higher acceptance rate distribution, and the position 6, they have a relatively low acceptance rate, and it corresponds with the position dependency, right? However, if we look at the specific position, like P1, we can see that different tokens have different acceptance rate, and it varies a lot, right? Some tokens have near 0 acceptance rate, and some tokens have near 100%, right? And what is the reason behind this phenomenon? And it is because different tokens have different context, right? Because they are of the same position, and the only difference is the query is the previous context of the token. So here is a basic example of this context dependency. And we can see that in Eagle1 only consider a static draft tree. It means that the whole draft tree architecture is fixed. When whatever the context is, like 10 plus 2, the next token can be equal or plus. And if we consider a different context, 10 plus 2 equal 2, and if we consider this equation, we could see that the next token, it has a high possibility to be 1, right? Because the result would be 12. And in this scenario, maybe we should not consider the token 3, right? Because 3 has a very low possibility to be predicted. However, in the Eagle architecture, it applies a static draft tree. So whenever the context, whatever the context is, it will always explore both the draft candidates. And in Eagle 2, it mentions that we should always keep in mind of the context dependency, and we should adjust the draft token tree architecture based on our context. And in this way, we can allocate more capacity, more computing resources to explore the tokens with high possibility to be accepted. And in this scenario, we will abandon the token 3 and explore token 1 and its subsequent token 2, right? And in this scenario, we can get 2 tokens accepted. And in this, with the same draft token capacity, right? We verify 2 tokens. And in this scenario, we only get 1 token accepted. However, in Eagle 2, if we adjust the tree architecture, we can further increase the draft token that get accepted. Okay, so here is another research question. It is, how can we know the acceptance rate of draft tokens in advance, right? Because during the inference process, we do not know which draft tokens they will have a high possibility to be accepted by the verifier model or the original large language model. And how can we estimate the acceptance rate of draft tokens in advance? Or in other words, how can we estimate the value of draft tokens so that we can put more efforts on the high value draft tokens? And in the work Glad of Cape in the ECMO 2024, they find that the confidence of the draft model has a high relevance with the final acceptance rate, right? If the draft model has a high confidence of its prediction, like the top one prediction, it has a confidence higher than 20% or 90%. And finally, we can find that the final acceptance rate of this draft token is also up to 90%. So it is a good kind of estimation, right? We can just use the confidence of the draft model as an estimation of the value of draft tokens. So this is exactly the core idea of Eagle 2. And the Eagle 2 is, as far as we know, it is the state-of-the-art method in speculative decoding right now. And the Eagle 2 and the Eagle 1, the authors are from the same team, right? So the core idea of Eagle 2 is how to filter out low-quality draft tokens. And if we are given a fixed length of draft tokens, we should allocate more computing resources. We should allocate more efforts on high-quality draft tokens. So how can we estimate the value of draft tokens in the original tree? We just get their confidence of the draft model, and we get the dot product along the whole path from the leaf node to the root node. It is very simple, and then we can get the value of each draft tokens of each node, and based on this value, we will rank the whole tree, and we find the draft tokens in gray ones. They have very small value, and we filter out these tokens. And if we are given the fixed length, it means that if we filter out these low quality tokens, we can investigate more on the high value tokens, so that maybe we can get more tokens to be accepted. So here is the experimental results of Eagle 2. We can see that compared to Eagle 1, Eagle 2 brings up to 20% to 40% speed up improvement compared to Eagle 1. Eagle 1 is previously state-of-the-art method in speculative decoding. And we should note that Eagle 2 is a quite elegant idea, right? Because it does not require extra training of the original model, right? It just adjusts the draft tree, and it can be seen like a plug and play method, and directly brings quite promising speed up improvement. So in our recent evaluation results, we can see that on the evaluation method, SpecBench, Eagle2 achieves relatively higher speed up, right? And it is now ranking first in our leaderboard. Okay. And here comes the last part of our cutting edge algorithms. Well, if we take a look back at this leaderboard, we can see that speculative decoding methods, they receive a lot of research interest, and this promising research area, it has very advancements in the recent years, particularly in the last year. And we can see that the speed ups gradually increases from the beginning of the last year to the end of the last year, from 1.4 to about 2 times speed ups compared to Vacuna. It is acceleration record of Vacuna 7 billion. And we can see that the mean accepted tokens, it gradually increases. And mean accepted tokens means that the average draft tokens that get accepted in each decoding step. And if we ignore the drafting latency, and we also ignore the verification latency, if we ignore all the latency, only considering the latency of the forward pass of the large language model, the mean accepted tokens is just an estimation of the final speed up, right? If you get more tokens to be accepted, you can leverage or utilize more parallelism in a single decoding step. However, we can see that the number of mean accepted tokens, they're reaching their upper bound, and the increasing speed of this metric is smaller and smaller. And we can see that speculative decoding, maybe it is gradually approaching the upper bound of the speed up, right? And we researchers gradually agree that under this speculative decoding paradigm, right, you use a small model to align with the target large language model, the bigger ones, the best achievable speculation performance, maybe it is an average of 4 to 5 mean accepted tokens, right? Because you require the smaller model to be very accurate, it could speculate very well on the future behaviors of the target large language model. It is a very strict requirement, right? So we all agree that maybe the upper bound is 4 to 5 mean accepted tokens. And if we ignore the verification latency and the drafting latency, maybe the upper bound of the speed up is 4 to 5 times speed up, right? And as we just introduced, this upper bound, the reason behind this upper bound is the strict verification requirement of speculative decoding. Well, we would always like the outputs to be exactly same to the original large language model, right? Because we want the outputs to be reliable. We do not want any change in the outputs. However, in recent years, the large language model have gradually improved, right? And we know some days ago, Tsinghua University, they released a dancing law paper, right? They say that the Llama 8 billion model, they have very promising capacity in recent days. And if we still conduct this kind of strict requirement, right? If we have a Llama 8 billion, like the smaller model, and the Llama 70 billion, like the teacher, like the verifier or the target large language model, maybe we should not strictly require the Llama 8 billion to output the same predictions to the target large language model. Because if the 8 billion paper are quite well, right, it contains a lot of high quality drafts, and we should not reject these draft tokens, these high quality draft tokens, simply because they are different from the original large language model, right? And in this promising work, charge decoding, it is the most recent research work in speculative decoding. It is a clear 2025 submission, and it is still under review. the reviewers, the authors, they conduct a very interesting study to see that under this equality requirement, right, the most strict requirement in speculative decoding, which requires exactly the same outputs, they investigate under this very strict requirement, how best can we achieve to build an optimal draft model? Well, they first replace the draft model like Llama 7 billion to human written text. You know, human experts, they are very strong, right? And they produce high quality tokens. And even we replace the draft model with human expert, we can only obtain 3 tokens past the verification. It means that even you utilize a human expert as a drafter to speculate the future decoding steps of the target large language model, you cannot do an excellent job, right? But maybe your job is not, your work is not so well as the Llama 8 billion. And the second experience is that they switch over the draft model and the target large language model. Well, in the left panel, the draft model is 8 billion, and the target model is 405 billion. It is very large. And we utilize the 8 billion to speculate on the future behaviors of the, this larger model. And we obtain a kind of six tokens that pass the verification. And if we switch over, we utilize a very large model as a drafter to speculate on the future behaviors of a relatively small model, a very small model, 8 billion. We can also get 6 tokens that pass the verification. Well, we can from these observations, we can see that no matter how strong or how big your draft model are, it has an upper bound of speculation accuracy or tokens get accepted in this strict requirement, right? And it is not right? Because if we have a human expert or if we have a very large token, maybe their output are of high quality and they are reliable, and we should put more trust on their outputs. So if we still rely on this strict requirement, maybe it is not correct. And the third experience is replace the draft model with GPT-4o. GPT-4o is a very large, very powerful model, like human expert, right? And they use GPT-4o to speculate the results of Llama 405 billion, and the performance is very awful, right? They only get an average of 2 tokens that pass the verification. Okay, so the finding is that no matter how strong the draft model are, under the strict equality requirement, we can only get a small or very few tokens that pass the verification, right? Like in this example, we can only get 2 tokens in the green part that pass the verification. However, if we look at the results, the outputs, we can see that the subsequent sequence is of high quality too. However, we just abandon this, we just discard this because they are different from the original outputs. And in this work, judge decoding, it reminds us that we should not stick on the strict requirement of speculative decoding. And we should always keep in mind that the final goal of speculative decoding is to accelerate the inference process with high quality outputs, right? We should always keep in mind is that our goal is that our outputs should be of high quality. They should not be strictly required to be equal to the original outputs of the large language model. And in this scenario, maybe we should change our requirement. We could require the outputs to align with human judgment, not the target large language model judgment, right? Because the outputs, the AI service serve for human life, right? Not the target large language model. And in this way, if we apply the verification model to be 405 billion charge, the judge verification means that we replace the strict verification requirement with judge verification with some kind of verification strategy that align with human judgment. And in this scenario, a large part of draft tokens pass the verification, like 2 tokens in strict requirement, or a large bunch of tokens like, I don't know, 20 or 30 tokens that pass the verification. So the key challenge of this human judgment is that how can we automatically estimate the human judgment? Because if we verify these tokens by human experts, we can always do. But in an automated process, we can train a model to estimate our human judgment, right? So the authors just they make a small data set, like 500 high quality question with correct answer, with wrong answer. And these answer pairs are maybe the ground truth and the outputs from Llama 8 billion or Llama 17 billion models. And they just ask some human experts to judge the outputs. If they are of high quality, if they are what we want from the query, from the large language model, and if the human expert find some parts or some tokens that are not correct to human judgment, they will just label these tokens, and the tokens subsequent will be regarded as wrong tokens. So by annotating these 500 data pairs, they train a very simple architecture. Well, compared to the vanilla, the Medusa architecture, we have multiple language modeling height. They just add a judgment height. The judgment height does a regression work, right? If we have a lot of tokens, a lot of draft tokens, except for the original verified token by the original large language model, they train a judgment height, a regression height to get a score of each token of its human judgment value, right? And this value is from 0 to 1. And if we get 0, it means that this draft token is not passed by human judgment. And if we get 1, it means that this draft token is highly aligned with human judgment. And in this, with the cooperation of this judgment height, we can release, or we can have a soft requirement of the verification process, right? So if some draft tokens, they fail the verification, the strict verification of the target large language model, however, it passed the verification of human judgment, we can consider this token as accepted, and we just include these tokens into the final output. So it is a kind of release or relax strategy, right? And this kind of method is quite simple. And by doing this, we can further investigate the potential of speculative decoding, right? Compared to equal to 70 billion that with the strict requirement, only about 4.5 tokens that get accepted. However, if we add this judgment height, over about 20 tokens can pass the verification, so that we can largely increase the speed ups. Okay, and finally, the authors investigated if judge decoding, if we relax the requirement, it will whether influence on the output quality. And they compare the 70 billion judgment with original 70 billion. Original 70 billion, it means that we conduct the strict requirement. And we can see that over various scenarios, their quality are similar, right? And if we further relax the requirement, we only require the draft token to drop in the top K predictions of the target large language model. The output quality will be degrades largely, right? Like the orange one. So in this experiment, the authors prove that the human judgment is quite aligned with the output quality of the generations, they are aligned with the original large language model. And maybe their contexts are different, but their quality are similar. Okay, so here comes our takeaways. Well, we should always keep in mind that in speculative decoding, in such kind of acceleration paradigm, we should always consider both metrics, the speed ups and the output quality, right? So like we previously mentioned, we should select high quality draft for verification. Although the verification process can be done in parallel, we should always utilize more high quality draft tokens in a fixed verification length so that we can achieve a more accuracy latency trade-off. And the second takeaway is that we should not get stuck in the draft verifier alignment. We should not stick on the strict requirement of the verification. We should always think that what is our final goal? Our final aim is to speed up the inference with high quality outputs. This quality should be judged by human experts, by the person that we want to serve, right? So the standard of high quality outputs should be judged by humans themselves, not the target large language model. And with this in mind, maybe we could further release the potential of speculative decoding. Okay, and next I will pass it on to my colleague Yongqi to part 4. Okay, thanks.
Okay, thanks to my teammate He for his excellent presentation. I'm Yongqi. I will now continue by sharing some downstream applications of speculative decoding. Okay, so the first thing I want to address is that speculative decoding is not just for the large language model, right? Actually, it is for autoregressive generation. Okay. We can imagine that even a small language model can benefit from speculative decoding to speed up its autoregressive generation progress. Okay. And also the most advantage of speculative decoding is it's lossless. It is a lossless acceleration. Okay. So if you have some requirement in accelerate the autoregressive generation progress and want to keep a high generation quality, you could try speculative decoding. Okay. The second point I want to address is that due to the big success of large language models, the autoregressive paradigm has been much explored in other areas, including computer vision, such as autoregressive image generation and autoregressive object detection. Okay, and also in information retrieval, the generative retrieval and the generative recommender systems are also proposed to satisfy users' information needs. So since this progress involves autoregressive generation, speculative decoding methods, of course, could be used to accelerate them, okay? However, in some special scenarios, new challenges and issues need to be addressed. Okay, first, let's move on to the application of speculative decoding in generative recommendation. Okay, first let me provide some basic background on recommender systems and the generative recommender system. Okay, so recommendation is fundamentally a matching problem. Okay, it aims to match the user with the items that they may prefer. Okay, the items may be videos or products. So as illustrated in the figure, traditional methods often approach this as a representation learning problem. Okay, it aims to learn the similarities between the user and the item in a common space. Okay, so this is recommendation. And another thing I want to address is that the goal of recommended system is to identify top key items. So because, for example, when we browse the video websites, we often receive a list of recommendation rather than just one single item, right? So this differs from text generation. And okay, now I will present a simplified framework to illustrate how generative recommendation works. Okay, so generative recommendation reformulates the original recommendation task as a generation problem. So specifically, so I saw in the right figure, the input could be the sequence of user behaviors. So maybe the names of the items that a user clicked, okay, and the output is the item. So more specifically, it could be the names of the items. And in this way, generative recommendation reformulate the original matching problem as an autoregressive generation problem. Okay, so another question that remember the recommended system require the top key prediction. Okay, so in generative recommendation, the beam search is applied to obtain the top key result. Okay, this is the generative recommended system. Okay, so since generative recommendation is typically an autoregressive generation process, right? So we can use a draft model to accelerate the target model. So there is no doubt. However, the usually speculative decoding faces challenges with the N2K verification in the generative recommendation. Okay, so let's first revisit the verification process in the text generation. So it is an N2-1 verification, right? So this means that the draft model can process N candidates, and if one candidate is accepted by the target model, yeah, we could regard it as a success trial. For example, in the left figure, the draft model proposed 3 candidate sequence, and if there is one sequence it's accepted by the target arm, so it could contribute to the speed up. Okay, but in generative recommendation, remember that we aim for the top items, right? So according to the previous policy, the draft model, yeah, must include all of the top key predictions from the target model in its N proposals. So for example, in the right figure, the draft model, yeah, this part is the beam search process of the draft model, and it will result in 3 candidate sequence, A1, B2, C1, A1, B2, C2, A4, B3, C1. And the target model, yes, of course, this is its beam search process, and its target, the target top key results may be A1, B2, C1, A1, B2, C2, and A3, B3, C1. So the draft model generates 3 sequences, but only 2 sequences are accepted by the target model. In this case, all of the 3 candidates are rejected. So it will result in a failed attempt. Therefore, the accepted rate of is much lower under the N2K verification. Okay, so under the strict verification, there is still something we could try to enlarge the speed up. Okay, so initially, the draft model was expected to generate a single target token at each decoding step. Now, it is expected to produce a set of top key tokens at each decoding step, right? Therefore, we could use the reverse KL divergence to align the token distribution with the target model. Okay, so now I just give a concept. So actually, the authors divide the distillation objective from the verification strategy. Okay. And the second try is to relax the verification. Yeah, because the previous strict N2K verification, now we could relax the strict verification specifically for the non-top K draft sequence. We could like have a certain probability to be accepted. Okay, so and correspondingly, we could design objective, distillation objective for the draft model effectively aligning with the target model. Okay, so the TVD distillation objective could be applied to align with the top K RM generated sequences. Okay, and for now we have two verification strategies. The first one is strict top K verification. So it is lossless, but should perfectly match to be accepted. And the second verification strategy is non-top K sequence. It can still be accepted by a certain probability. Okay. And we also have two corresponding alignment training. So the first one, optimizing the acceptance rate and the strict top K verification while the KL divergence distillation. And the second alignment training, okay, it is conducted by the TVD objective. Okay, and from the left table, we have the following observations. So first, if we adopt the strict verification, okay, the corresponding distillation method, the AT speed ice is preferred. And on the other hand, if we adopt the relaxed verification, the corresponding alignment training is preferred. Secondly, both of these combinations better than the standard sequence distillation. Okay, so all of the two combinations have a large speed up than the traditional method. And the third observation is that AT speed gun R shows a lower speed up at record 1 and record 3, but achieves a higher speed up at record 20. So this is acceptable, right? As recommendation system typically prefer good top K results over top 1 results. And now let's move on to the application of speculative decoding in autoregressive image generation. Okay, so firstly, an image can be represented as a sequence of visual tokens. Maybe we could call it tokens. Okay, so in the left figure, yeah, a typical image tokenization method of VQ-GAN, okay, where a codebook is learned, and each entry in the codebook corresponds to a visual token. So an image could be converted into a sequence of visual tokens where the image tokenizer. And conversely, a sequence of visual tokens can be transformed into an image where the image detokenizer. So in this way, the text-to-image generation could be modeled as token-to-token autoregressive generation problem. Okay, I saw in the right figure, in the training stage, the input is the tokens of the caption, and the output is the corresponding visual tokens of the target image. And in the inference stage, we could input the text and let the generation model to predict the visual tokens one by one, and then the predicted visual tokens could be transformed into an image. Okay. So the autographic image generation is a typically autographic generation process. Of course, we could use a small draft model to accelerate its generation. Okay, but let's see the result of the straightforward application of speculative decoding. So there are three speculative decoding methods, including the Medusa and the equal2. Okay, and the mean acceptance is reported to measure the speed up performance. Okay, the LangGen is an autographic image generation model, and the Vicuna is a text generation model. So from the table, we can see that the straightforward use of speculative decoding results in a poor performance. Okay. So, but why? What's the difference? Why is there a significant difference in the speed of advancement between the text generation and image generation? So let's see a simple experiment. Okay, in the left figure, the top 1 and top 10 probabilities of the two generation models are reported. So the Vicuna is the text generation model, and the LangGen is the image generation model. Okay, we could find that LangGen has significantly lower top 1 and top 10 probabilities on average compared to the text generation model. Okay, so it means that there is a great ambiguity in selecting the next token in the autographic image generation models. So in other words, in the autographic image generation model, it prefer assigning the average probabilities to the visual tokens. Okay, so it is not much confident compared with the text generation model. So the authors referred this as token selection ambiguity problem. So how to solve this problem? Yeah, as an old saying goes, whoever hung the bear on the text neck must untell it. So let me explain it. Okay, so this is the result of some generation results from the autographic image generation models. Okay, the first row is the standard sampling method. For example, we could let the autographic generation model to predict the image with graded decoding. And the second row is randomly replace the visual tokens with some closed tokens in the latent space. Okay, so is there a large change in the quality of the results? Actually, we can't sense it from our eyes. So this states that the slight change in the latent visual tokens do not significantly affect the outcome. Okay, actually it's reasonable, right? Because if we just have a slight change in the latent space, because after the transmission of the image decoder, the outcome will not be affected very much. Okay, so the conclusion from this simple experiment the tokens that close in the latent space can be treated as interchangeable. So it allows for the flexible token replacement without significantly compressing the visual semantics. Okay. And based on the above findings, the solution is obvious, right? So this formula, the original speculative decoding could be formulated as follows. Okay, the P is the draft model and Q is the target model. So this formula represents the probability of the token of the generated tokens from draft model that can be accepted by the target model. Okay, so we could simply reflect the acceptance condition. We could by integrate the neighbors of the predicted visual tokens. So the BK represents the bank of the neighbors of the predicted visual token X held in the latent space. So from this formula, we can imagine that the acceptance rate could be largely improved. Okay, so how about the result? And from this table, yeah, the compared method including the vanilla autoregressive regressive equal to, and the metrics including the speed up and the mean acceptance length. So these two metrics is about the efficiency, and the FID and the clip score could reflect the generation quality. So a smaller FID represent a better result, and a larger clip score represent a better generation result. So from the table, we can see that the speed up is significant compared with the speculative decoding in the text generation. And we can also find that the quality cost is slight. In terms of FID, there is only a slight increasement. Okay, the final part of this tutorial, final remarks and outlook. So I summarize some trends in the speculative decoding. First, from multiple models to a single model. Okay, in the conventional speculative decoding, there are two standalone models. Okay, one is the draft model and another is the target model. So I believe it is not convenient if we need to deploy two models in practice. And now we have the chance to conduct speculative decoding with one single model. For example, where the techniques like multiple token prediction and layer skipping, we have the chance to transform the target model as the draft model itself. Okay. And the second trend is that from training to pre-training or non-training. Okay. So to obtain the draft model in the traditional speculative decoding, yeah, we usually need the alignment training, okay, between the draft model and the target model. So essentially, it is a distillation process. This means that we must leverage data samples to achieve the predictions from the target model. However, the data samples can't cover all of the situations. This means that there are always corner cases in the alignment training stage. Okay. And the second point about the training of the draft model. So actually there are many large language models, right? Different models and different sizes. So each large language model may require a corresponding alignment training to achieve an effective draft model. So it is obvious a waste of the training resource, right? So now the training is that first transfer the training to the pre-training. So we could imagine that if the large language model, for example, it could has the ability to predict multi-tokens in each decoding step in the pre-training stage. So if it is released the large language model, we don't need the training of the draft model, right? Because we could just use the large language model itself as the draft model. Okay, and another solution is no training. Okay, for example, we could mask some layers in the target model and regard it as the draft model. So in this way, we don't need any training in the whole process, and we could perform the speculative decoding. Okay, the third trend is from strict verification to relaxed verification. Okay, so actually there is an upper bound of strict verification. Okay, because basically we require the draft model is more efficient than the target model. So therefore, it must be less powerful than the target model. There is no free lunch in the world. So the upbound, there is upbound of the speed up. Okay. But okay, now we could rethinking the meaning of lossless. So lossless is the most important feature in the speculative decoding, right? But now we could rethink it. Originally, the lossless is defined by the target model. It means that if the draft model predict the same result with the target model, we define it as a lossless acceleration. But do we need so strict verification process? I think the answer is no, right? Because, for example, a large language model, I could ask it, where is the code in 2025 be held? Maybe it could directly give the location Abu Dhabi, and it also could give a sentence. The code in 2025 is held at Abu Dhabi. So both the two responses are qualified, right? So from this example, we could redefine the lossless from the user perspective. So if we don't have don't sense the quality change, we could regard it as a lossless acceleration. Okay. And finally, yeah, you could access our slides and maybe the recordings from our tutorial homepage. And thanks for my teammates for today's tutorial. Okay, maybe finally is a question answering part. So if you have any question, just be free to propose. Okay.
Okay, thank you guys for listening. So are there any questions? Sorry, can you speak louder?
Can you hear me now?
Yeah.
Yeah.
So, have people tried using approved version of the larger model for generating the draft tokens, just pruning the larger model by like removing layers or just falsifying it. Is that better than using a smaller model from the seed?
Sorry, I beg your pardon. Do you mean that do people use approved version of large language models for drafting?
It's like how does that compare to using a smaller model which was pre-trained from scratch? Is it better or is it just worse than that?
When you say improved model, do you mean that the model with instruction tuning or I do not know why you compare it with the model that trained from scratch.
To mean prune the models like prune a large model into a relatively small one.
Yeah, pruning by like removing layers or sparsifying it.
Okay.
Please keep.
Yes. I have tried some pruning on larger models, but I think usually you should spend a lot of tokens to training the pruned models to be act as a normal model, because after the first pruning, it requires some tokens to recover the language model generation capability. Usually I would suggest use a relatively small model if there are available models, but if not, you have to prune the model to train a smaller one. But I'm not sure about the speed up compared to other self-drafting methods.
And so right now, what's like the heuristic people use to decide how many tokens to draft? Do they like just draft, say 5 tokens, or is there a method to stop?
It is based on the capacity of your draft model, right? So if you get a strong draft model, maybe you can increase the capacity. You can let it to decode more draft models. And if you have a weaker one, right? If you draft, like 10 tokens or 20 tokens and only 2 tokens pass the verification, then maybe you should decrease the drafting capacity, right? So and there are many adaptive strategies in speculative decoding that proposed last year to adaptively fix the drafting length during the inference process, and we recommend you to use these papers.
I think that was one. Thank you.
Okay, thanks.
So any other question? Okay, so if there is no more question, I think we could end today's tutorial and enjoy our lunch. Thank you.
Thank
Okay.
you.
Thank you. And if you have any further question after this tutorial, you can scan our QR code on Slido, and we can discuss further in a few days.